days ago. Now you got 3.19 microcuries of radiation. What's that like?
It's fine. It's fine. Now what's happening? I'm gonna change.
My goodness. We're gonna figure something out. Can you see?
Chase gonna block you?
So first order kinetics means the rate law is that, right?
Okay, yeah.
First order kinetics means that the integrated rate law is this. And
Yeah.
first order kinetics means that the half-life equation is this.
Yeah.
Right? Because A over A2 equals 2. Okay? So those are your three master equations there. Well, that's your master equation, your integration, and your solution to the integral. Think of it as three equations if you don't know the calculus.
Got it.
So, what do we know? Let's go through the problem and identify variables. So what's this right here? What would that be on here? What would that be?
A0.
That would be AO. Okay. And what's that?
T.
So there's T. What's that?
A, T.
A sub T.
A, T, and T.
Okay. What can we solve?
Everything.
We can solve everything?
Okay.
Which one of those equations should we use right now? The middle one, right. So plug it in the middle equation, and that's going to give us K. So natural log AO over AT equals K times 4 days. At that point, we need a calculator. I don't know what the number is.
It's small.
It's what? 0.002. And what would the units be on that? Well, let's see. This is microcuries, and this is microcuries.
They cancel.
So what units do I have over here?
Nothing.
I got nothing because they divide out, right? So that means I can't have units over here either.
No.
So what does this unit have to have for units?
Per day.
Yeah. Right? Because day times per day is going to give you nothing. Right? Okay. Okay, so I got K. Now what can I do? Now I can solve for the half-life.
Yep.
So now I go natural log of 2 equals 0.002 per day times T1/2. And at this point, I would just point out to you, because I don't know where we actually ended up on the calculator. 0.002 that he told me there, that may very well be rounded.
It is.
Okay, that I'm sure it is. So don't use the rounded number when you go on down the road, right? Use the actual number. Significant figures only apply when you are reporting the number. They have nothing to do with the calculations,
Yeah.
right? So calculate, you want to keep 13 digits when you do the calculation, that's fine, nobody cares. It's only when you get to that final answer and you're actually telling me what the answer is, at that point, now give me the right number of sig figs, right? Okay. All right, so, I don't know, what do we get?
I got 296 days.
296? Cool. 296 days. There you go. So we're able to figure out what the half-life is.
About 10 minutes.
Okay. These are the only two integrations that we're going to use in this class. Okay? You may have rate laws, we may have this equation that we'll do for zero order, second order, third order, fourth order, fifth order, whatever. But we're not going to do any of the integration type stuff for anything except first order reactions. And I think I mentioned this before, but I'm going to mention it again because she's recording me, so I want to make sure it's mentioned. Okay, so, but only first order half-lives are independent of the amount of stuff you have. All the other just a second, I'll be right there. All the other half-lives are dependent upon how much you have. So the half-life of a second order reaction is different if you start with 100 as if you start with 50, which means that nobody uses it because it's idiosyncratic to the specific experiment you did. So nobody cares, right? So I showed you how to do it just because it was an integration and it kind of showed the pattern of what was going on. But as far as problems in class, we're never going to use them. Okay, question?
So for the second and third rate law, are we gonna ever use those integrations, or is it only for the first one?
We'll only integrate for the only time that you're going to have anything that deals with the integration was on the graphical method of analysis where I said, what are we graphing? We're graphing 1 over a or 1 over a squared or 1 over a cubed or something like that. But that doesn't require you to actually know how to integrate, right? That just, you need to know that it's one less than the power that you're, of whatever. So you'd have that, but not the actual integration itself. Okay, so there's that. We've done the method of initial rates also. So what I want to do is continue on with my discussion about energy. I've got two graphs here. So if here's my reactants and here are my products, way back in late 1800s, people knew that there has to be a barrier between reactants or products because we know from just heating up a piece of metal, we know that heat flows from hot to cold. So from high energy to low energy, you always have the heat flow from high energy to low energy. That's just the natural way the universe works. But the fact that your high energy reactants does not flow to your low energy reactants spontaneously means there has to be an energy barrier here. And so that barrier is the activation energy. So that is the activation energy. This point right here is called a transition state. Think of it like this. Let's say that, take a real simple one. Let's say that hydrogen and iodine are reacting together, okay? So I have my H, and I've got my I that have to react. And for them to react, do you remember what has to happen? They have to collide. So they have to collide. And when they collide, you're going to get some sort of weird something like that as they hit and bond together, right? And so this is this very unstable, because that doesn't make any sense. This is that very unstable transition state. They collide to form this high energy, unstable thing that then is allowed to fall apart. And who knows, it's probably more like this. Probably something like this. Yeah, probably something like that. I haven't studied that reaction, so I don't know what the transition state looks like. But so it forms this high energy transition state. So here's your transition state. This guy does not want to exist, but it has to because they have to collide. And then it immediately collapses into two of those. So here's your H2 and your I2. Bam, it comes up here. It turns into this weird transition statey kind of thing that all kind of gloms together. And then that immediately falls apart and boop, down there to the products. And that is typical of what happens in any reaction. So this hump, if you will, is these guys colliding together and turning into something unstable that will then fall apart into something else. Okay? Does that make sense?
Yeah.
Okay. Now, Arrhenius said that if you take a look at that, if we look at your bell curve here, let's say this is EA, is right there. Hopefully you can see that since molecules follow a bell curve, the bigger this hump is, the farther down this line that moves, right? And so, you know, if we say, to get into a TCC, you have to have a 14 ACT. Well, look, the population that can get into TCC is awesome. It's huge, because you need a 14. If on the other hand, you want to go to Northeastern, you got to have an 18 ACT. Okay, some people can get into TCC but can't get into Northeastern. To get into OU, you got to have a 22 ACT. Now you have fewer people that can get in. You know, to get to TU, you have like a 26 or something. So you see how the higher that hump is, the more you have to have, the more energy it takes to get to this transition state, the smaller the reaction is going to be, because the fewer collisions are going to meet this criteria right here. You can have fewer and fewer things that can meet the criteria. To the point where, and I think we mentioned this on Monday, where I showed you like the diamond to graphite one, where you have this huge transition state to go from diamond to graphite, which means that there's so few molecules over here, you know, that you just can't hardly do it, you know? So to go from diamond to graphite, to keep our example, you not only have to have an ACT of 36, but you also have to have an SAT of 1600 and a 4.3 GPA and have won a major national prize. Well, okay, not many people meet that criteria, right? And so it's really hard to get over that transition state, and so there are very few molecules that can do it. Realize that when I say very few molecules, I mean population of the United States per second, but that's a teeny tiny number of molecules. Right? Okay. All right. So that's what a transition state is. And that's why, and that makes it very clear at that point that there is a relationship between how many molecules can react. These are the molecules that can react. These are the only ones that can collide and make a productive collision. Okay? But realize both of those molecules have to be on that side, right? To get up here. So hopefully you can see that as I heat the sample up, more molecules have the energy to get over the transition state. And so that fits with what we actually know, right? If you heat up a reaction, it tends to go faster. You want to cook a hamburger, you cook it on high versus cooking it on low, it's going to cook faster on high. Because more molecules can get over the transition state. More molecules have the energy to make it over the EA. Now, I actually don't remember whether I talked about this before, so whatever. I'll pretend like I hadn't. The guy who came up with that original idea was Arrhenius. And Arrhenius, he described this curve, which actually can be described mathematically. This is a well-known the mathematics of a bell curve are well-known. I'm not sure they were well-known in 1880, but whatever, they're well-known now at least. And he said that this is the governing math that describes that equation. And so he said the rate constant, because that's going to be the rate constant, K, is equal to what's called the frequency factor, which is how many times does H2 and I2, how many times do they have to collide before you actually get that transition state? So maybe H2 and I2 collide 1,000,000 times before you finally get one where it goes, oop, that's right. You know, it's like, how many dates do you have to go on before you find somebody you actually want to hang out with forever? You know, it's kind of like that kind of thing. So, and it's based also on the activation energy. You'll notice that the bigger activation energy, the smaller K is going to be, because the bigger the activation energy, the harder it is to get over this hump, right? So this is his equation, which got him in huge trouble, but whatever. So how is this useful to us? Well, I'll show you how. K we can find from over here, right? I mean, that's the same K. It's that right there. And it's this K. And so all reactions have a K. Whether it's first order, second order, third order, 10 reactants, or 2 reactants, it doesn't matter. They all have a K. And that's the K we're talking about right here. That's that K. So this and that are the same thing, right? Well, if you want to get rid of E, what do? You take the natural log, right? So let's do that. Let's take the natural log of this. So you guys know if you take the natural log of one side, you got to take the natural log of the other side too, right? Yeah. That's just how. Okay, so here we go. So natural log of K is equal to the natural log of A. Remember, if you take the natural log of A times B, that's natural log of A plus natural log of B, right? That's a log identity. So you end up with that. Well, let's do the same thing we did with the method of initial rates. Remember when we had all those extraneous variables we didn't want in the method of initial rates, so we held one constant and we got rid of the K's and one of the variables so that we could actually figure out what we wanted. Let's do the same thing here. Let's do 1 and, well, that's a constant, so it's not gonna matter. That's a constant. That, I guess that's gonna change. Let's just do this and divide it by another one. Oop, W2. Because one of the things that comes out of the Arrhenius equation is that this rate constant is temperature dependent. You see that? Mm-hmm. EA is a constant for any given reaction because it takes that much energy for hydrogen and oxygen to react. But the temperature actually does matter because that's what shifts this whole thing this way. So I can divide these out and notice what happens. A goes away. That's awesome. What is log K1 divided by log K? Oh, hold it. I'm screwing up. Forget what I just said here. We're going to do it differently. I need to subtract. Because I forgot my log identity. You got to subtract to get the division.
Yeah.
Okay, so we're going to subtract these two. So we end up with log K1 minus log K2 equals log A minus log A. Well, that's going to cancel out, right?
Mm-hmm.
And then we have, let's do this, minus EA over R. Let's pull that out. And then what do we have? 1 over T1 minus 1 over T2. Right, pull EA over R out of here and then subtract them, that's what you would get, right?
Yeah.
So we cancel that, so that goes away, that's good. What is log K1 minus log K2?
Log K1 over K.
Log A minus log B is log A over B, right? Log identity?
Yeah.
Okay, so that's log K1 over K2 equals, remember my rule? I got negative signs I can get rid of, let's get rid of them, okay? So let's multiply by -1 to get rid of the negative signs. So it's equal to EA over R, but now it's 1 over T2 minus 1 over T1. Now I want to show you something about this log thing. So here's my base equation after I log it, right? Right?
Mm-hmm.
That's, I just pulled the EA over R out of the fraction. Look at this. Oh, that's a line. Which means that if I graph, okay, what's my graph gotta be? What are my axes on my graph? What's my y-axis?
L and a K.
Log K. What's my y-axis? I mean my x-axis.
1 over T.
1 over T. And where's my y-intercept?
Ln of A.
Ln of A. So my y-intercept here is log over A, and the slope of my line is EA over R. Yeah.
When you multiply by -1,
Yeah.
you need to flip your case.
Oh, I may have to, let's see, log K2, K1 over K2 minus, well, let me see here. Minus EA over R minus EA over R 1 over T2. No. That's how that actually works out, right? And so that's where your minus comes from. So you end up with EA over R times 1 over T2 minus 1 over T1. Right? You're right, if I had actually multiplied by -1, I would have to multiply this by -1 also, right? But I didn't actually do that. I actually took advantage of the minus that was here, and I have a minus. That's where it comes from, right there. Yeah.
Thank you.
Oh, and that's minus EA, So notice what this is right here. That's simply a 2-point slope method of finding the line. That's all this is, right? This is y2 minus y1 equals x2 minus x, whatever, whatever that formula is for finding the slope. So notice the assumption there is that both the data points are on the line. If, however, you collect decent data, that's a reasonable thing to do, to say. And I would point out that this is 1 over t. So 1 over 273, that's freezing. That's boiling. Not really a very big increment on that graph, right? Because we're not getting down to where it really changes fast, like, around absolute zero. So, so this graph, while it's absolutely true and everybody agrees it's absolutely true, if you don't have a reaction that you can do at a really big temperature range, it's not practical to do it this way. And so almost everybody does that and just says, we're gonna take 2 points, and now we don't care what the separation is, because if we make the assumption they're both on the line, it doesn't matter if we're taking this point and that point, it's okay. Right. Okay, so this is if you're just saying, give me the stinking equation so I can pass the test. Okay, there it is, that's the equation. And that's the reason. Okay, so let's try a problem. Proofs in the pudding here, right? This is one of those where we're gonna see algebra mistakes. So we'll see if you can negotiate. So a reaction has a K equals 0.00034. One thing you will want to know is you're going to want to be using this, because EA is an E, which is in joules, right? That's an energy, so that's in joules.
Oh, I can't see, sorry.
The same R that we use in the electric chemistry. We want the one that's got joules in it. What are we going to call 1 and what are we going to call 2?
Two.
Does it matter which one I call 1 and 2? No, not really. But which one do you want to call 1?
The first one.
First one? Okay, we're gonna call this 1.
Thank you.
So this would be T1,
Yeah.
and this would be 2, and this would be T2, right? So let's just plug our numbers in. So log 0.00034 over 0.00041 equals EA over 8.314 times 1 over T2
363.
minus 1 over T1
Yep.
solve for EA. Now, let me remind you of something. EA is the barrier between reactants and products, right?
Mhm.
Can EA be negative?
No.
No, it's the hump. So it's quite common to make an algebra mistake. One of the signs you made an algebra mistake is you get a negative number for EA. Okay? That probably means you got your T1s and T2s mixed up or something like that. Okay, what do we get? 28.6.
48 for EA?
EA,
Yeah, I got 3.5 kilojoules.
Yeah.
3,500.
Yeah.
Yeah.
3,500. I hear a lot of 3,500. I'm gonna go with that. And I'll put it in kilojoules too, because you guys want it in kilojoules. Okay.
But we don't have to necessarily.
No.
It's just a better number.
Yeah. I mean, the usual rule of thumb for people is that if you can change the units to make it within fingers and toes, do it.
Okay.
Just because that's the way people think,
Let's
right?
just say like deci or something. Well, that's for us.
I mean, do you really sit down there and go, I have 2.93 billion bits in my hard drive? You go, I got 2.9 gig hard drive, right? That's what
Okay.
you do, because I wanted fingers and toes. I don't want to say 2.9 billion. Yep.
How do moles cancel
Huh?
out? How do the moles cancel out?
Divide those.
They're not really, it's gonna be joules per mole.
Yeah. That just makes sense.
Because this is joules per mole degree Kelvin.
Yeah.
The kelvins cancel here, the joules per mole over joules per mole cancel. So you're left with joules per mole over joules per mole, right? And then those cancel. Probably shouldn't do the diagonal slash. Okay. Now it's obvious they canceled. Okay. All right. All right. So you guys see how to do it?
Yeah.
I mean, that's how you do it. So that's how these that's how activation energy works. So how do I speed up a reaction? What?
Heat it up.
Heat it up. I can heat it up and that'll speed up a reaction. We all know that works, right? Because we've cooked at some point in our lives, I'm sure. But there's actually another way. And that's if we can figure out how to lower the hump. If we can figure out how to lower that EA, we can also speed up the reaction. That process of lowering EA is catalysis. Catalysts lower EA. They do what's called stabilizing the transition state. They somehow make this easier to form, so it doesn't take as much energy. A classic example would be the hydrogenation of vegetable oil, which, by the way, FDA just ruled last week that partially hydrogenated vegetable oil can no longer be considered a GRAS, generally recognized as safe material, because of trans fats. That's the major source of trans fats. So food manufacturers are frantically trying to get rid of Crisco out of their, well, not Crisco, but partially hydrogenated vegetable oils, trying to get out of there. Okay, we'll actually talk about that a little later because that's actually kind of cool. Okay, so catalysis. So let's do a classic catalysis, which is hydrogen. As a matter of fact, let's do partially hydrogenated vegetable oil. H2 plus some fat. Okay? The difference between an oil and a fat is a fat is a solid and oil is a liquid, right? The reason why an oil is an oil is because it's got that double bond. You take all the double bonds out, you make it into, you make it all single bonds, it's now a solid. So when you make margarine, you take corn oil and you get rid of the double bonds and you turn it into all single bonds, and now it looks like butter, except it has trans fats in it, so it's actually worse for you than butter, but whatever. Okay, so this is a very common process to do this right here. But I guarantee you, if you take corn oil and you bubble hydrogen through it, you have fizzy corn oil. You do not get a reaction. You just have bubbles of hydrogen in your corn oil. That's all that happens.
Yeah.
Because the energy barrier is too high. So what we have to do is we have to add a catalyst to it. And it's a platinum catalyst in this case. And if you think about, that's what it would look like. I mean, that's the corn oil right there. And then what we'll do is, in the presence of that platinum catalyst, it gets rid of that double bond. And now that it's a saturated fat, which means it's got as many hydrogens as it could possibly have, that's what saturated means, all single bonds. Unsaturated fat means it's got a double bond. So what's a monounsaturated fat?
One double bond.
One double bond.
Yeah.
What's a polyunsaturated fat?
Multiple double bond.
Yeah, because remember, one, lots. Okay, so more than one.
Yeah.
How many? I don't know, whatever. More than one. Okay. So when they say, oh, it's filled with polyunsaturated fats, it's like, great, I got fats that got double bonds. Okay, so this right here, though, requires a catalyst. When you have a catalyst, there are some requirements. It has to lower activation energy. It's got to speed up the reaction. And it can't be consumed. In other words, it's not a reactant or a product. So for example, an enzyme. You have the enzyme that's going to turn carbonic acid into CO2 so that you can breathe, okay? It catalyzes carbonic acid anhydrase, catalyzes the reaction of H2CO3 into CO2 plus water, but it itself is not used up in the reaction. You can keep using that same carbonic anhydrase over and over and over again because it's a catalyst. It's not actually part of the reaction. You see the difference there? Because I could speed up a reaction by just adding more reactants, right? Because rate equals Ka, right? I increase A, I totally increase the rate of the reaction. But that's not a catalyst because even though it sped up the reaction, it got used. It was a reactant, right? So typically, a catalyst is put on top of the arrow to tell you that it's in the reaction, but it's not a reactant or a product. It's a thing that allows the reaction to happen. Now I want to show you something kind of cool, or kind of bad, depending on your position on nutrition. So here's your reaction. You start with your oil, it goes like this, there's your normal reaction. And when you add that platinum catalyst, it does that. So here's EA, and this right here would be EA catalyzed. Okay? So my catalytic EA goes down. I don't think we have any PEs in here, but, or do we have any chemies in here? Chemies? Couple? Okay. This is one of the things that you run into in chemical engineering all the time. Like, for example, you want to turn petroleum into gasoline. Petroleum is like C40. It's got like 40 carbons. It's like tar-like. But you want to turn it into gasoline, C8s. Well, what do? You run it through what's called a cracking tower, which is simply a tower filled with catalyst. And as it goes through that catalyst bed, as it goes through that bed of catalyst, that C40 turns into 5 C8s. And coming out that pipe at the top is gasoline. And occasionally, because it's petroleum and who knows what it was made out of, it's just whatever crap came out of the ground, you may not be C40, maybe it's C41s. At which point it turns into 5 gasolines and some methane. And sometimes you'll see like a fire at the top of the tower at the refinery. That's them flaring off the methane that comes off the top of that tower. Because that was just what was left over when you got done. Was that right there? Okay. So I just want to show you what happens here. So we catalyze this reaction. We need to get that much EA to get over the hump, right? But look at our graph here. So here's our stuff right here. So let's say this is EA. But this is EA going backwards. Once I start forming product, can you see that some of the product's gonna have enough energy to actually go backwards? Once I actually have some, that's, by the way, why it's called the method of initial rates, because you want to find the rate before you start getting a back reaction. Well, because you've lowered the EA so much, you start to get a back reaction. If you have 3 places with electrons right here, what shape is that? 3 places with electrons. Gave you a test on that. Chem 1, that was your first test, right? So 3 places with electron, what's the shape? BSEPR, Vesper model. What's 3 places with electrons? What's as far away as 3 things can get?
1 point.
Trigonal planar, right?
Trigonal planar.
That?
Yeah.
Cool. So this is a trigonal planar structure. Like that. And naturally occurring fats are in this configuration. This is called cis. That's the cis configuration where they're both on the same side. Okay? However, after catalysis, this is now no longer enzyme derived. This is now in our manufacturing plant. This is actually has a higher energy than this configuration. Oops. And so when it recombines that way, and that's trans. And so we have cis fats are what come in, but trans fats are what come out. This is why partially hydrogenated vegetable oil is unsafe, is unhealthy, because you turn the cis fat some of it recombines the back reaction into a trans fat. That's a trans fat. Now, think about why that is. So here's a cis fat. It looks like that because it's making a bend like this, right? Makes a U bend. But this is what a trans fat looks like. But this is what a saturated fat looks like. These go into different pathways in your body. Oh, biology majors. Okay, so there's a separate pathway for this guy as opposed to this guy. So these trans fats look like saturated fats. They go into the saturated fat pathway and then go, crap, I don't know how to deal with this double bond. And it screws everything up because this is in the wrong pathway. That's why trans fats are bad, because the shape of the molecules is wrong. Pretty cool, huh? Yeah. All right, see you Friday.